In 1887, in the industrial heart of Cleveland, Ohio, the air inside a stone basement was heavy with anticipation. Two bearded men, Albert Einstein and Edward Morley, stood in the dim light, their eyes fixed on a heavy sandstone slab floating on a pool of mercury. They were not mystics, but they were hunting a ghost. At that time, the universe was believed to be filled with an invisible, weightless substance known as the luminiferous ether. It was the canvas upon which God painted the stars. Just as sound requires air to travel and waves require water, light, the physicists argued, must require ether. It was the absolute reference frame of the cosmos, the silent, stationary backdrop to Newton's clockwork universe. Michelson and Morley had built the most sensitive device in history, the interferometer, to detect the Aether wind as the Earth plowed through this invisible ocean. They rotated the slab, they waited, they measured. But there was no wind, there was only silence. Day after day, season after season, the result was a stubborn, terrifying zero. The speed of light remained exactly the same, no matter which direction the Earth was moving. It was the most famous failed experiment in the history of science. It was a crack in the foundation of the Cathedral of Physics. A whisper that suggested the great Isaac Newton might be wrong. But the scientific establishment was too afraid to listen. They patched the cracks with complex, desperate mathematical excuses, trying to save the ether, trying to save absolute time. While the titans of academia wrung their hands over the clouds, darkening the horizon of physics. A young man in Bern, Switzerland, was sitting in a patent office, bored. He was not a professor, he was a third-class technical expert, checking blueprints for gravel sorters and typewriters. His name was Albert Einstein. In the quiet moments between applications, Einstein stared at the clock tower outside his window and performed a thought experiment that would shatter reality. He asked himself a simple, childish question: what would happen if I chased a beam of light? Newtonian physics offered a clear answer. If you run forward on a train, your speed adds to the train's speed. Velocity is additive. Therefore, if you could fly at the speed of light, you should be able to pull up alongside a light beam and see it frozen in space, like a stationary wave. But Einstein knew this was impossible. He was haunted by the equations of James Clerk Maxwell, the father of electromagnetism. Maxwell's math was adamant. The speed of light is a universal constant. It is c. It does not care how fast you run. It does not care how fast the source is moving. It is the cosmic speed limit, unyielding and absolute. Here was the conflict that no one else dared to touch. Newton said time is absolute and speed is relative. Maxwell implied light is absolute. They could not both be true. Einstein made a choice of breathtaking audacity. He chose the light. In 1905, his miracle year, Einstein published the special theory of relativity. He declared that the Aether did not exist. There is no absolute background. But the price of this truth was terrible. To keep the speed of light constant, Einstein had to sacrifice the one thing we all intuitively believe in: time itself. He told the world that time is not a steady river flowing at the same pace for everyone. It is elastic. It is personal. If you move fast, your time slows down. Your watch ticks slower than mine. Your heart beats slower than mine. You age slower than me. Space and time are not separate stages, but a single, woven fabric, space-time. The academic world responded with a deafening silence, followed by private ridicule. How could a patent clerk tell the Royal Society that now is an illusion? But Einstein was not finished. Special relativity only applied to uniform motion. He wanted to understand the force that holds the planets in orbit. He wanted to rewrite gravity. For 10 years, he struggled in a mathematical wilderness. He realized that if time and space are a fabric, then gravity is not a force pulling objects together, as Newton claimed. Gravity is the curvature of that fabric. Matter tells space-time how to curve, and space-time tells matter how to move. In 1915, he unveiled general relativity. It was a theory of sublime beauty, but it made a shocking prediction. Light itself, which has no mass, must bend when it passes near a massive object like the sun. This was a direct challenge to Newton's divinity. Newton envisioned light traveling in straight lines. Einstein predicted a curve. The calculated difference was tiny, but the philosophical chasm was infinite. Who was right? The British genius who defined the laws of motion, or the German, Swiss theorist who had never performed an experiment in his life? Nature offered only one test, a total solar eclipse. Only when the moon blocks the sun's glare can we see the stars behind it and measure if their position has shifted. The year was 1919. The world lay in ruins after the Great War. Science, like the nations of Europe, was divided. Into this chaos stepped Arthur Eddington, a British astronomer and a Quaker pacifist. He believed that science should transcend borders. He organized 2 expeditions to prove or disprove the theory of a German scientist. One team went to Sobral, Brazil. Eddington went to the island of Principe, off the coast of West Africa. On the day of the eclipse, May 29th, a storm raged over Principe. The rain pounded against the tents. Eddington waited in agony. The theory of the universe hung on the whim of the weather. Miraculously, just as totality began, the clouds parted. Eddington frantically took photographs of the Hyades star cluster surrounding the darkened sun. He didn't know the result yet, but he had captured the data. Months later, in the Grand Hall of the Royal Society in London, the elite of British science gathered. A portrait of Isaac Newton looked down upon them. The atmosphere was tense, almost religious. Eddington unveiled the measurements. The stars had moved. The deflection was exactly what Einstein had predicted. The heavy, rigid bars of Newton's absolute space had been bent by the mind of a patent clerk. It was said that at that moment, Newton's portrait seemed to dim in the gaslight. The next morning, the headlines screamed, "Revolution in science, new theory of the universe, Newtonian ideas overthrown." Overnight, Einstein became the first celebrity scientist. He was no longer just a physicist. He was the man who had seen the mind of God. He showed us that the universe is not a rigid box, but a dynamic, warping dance of geometry. Today, a century later, this might sound like abstract philosophy, but it is not. It is intimate, it is in your pocket. When you open your phone to check your GPS, you are relying on a constellation of satellites orbiting 20,000 kilometers above you. These satellites are moving at 14,000 kilometers per h-hour. Because of their speed, special relativity dictates that their onboard atomic clocks tick 7 microseconds slower than clocks on Earth every day. However, because they are far away from Earth's gravity, general relativity dictates that space-time is less curved. And their clocks tick 45 microseconds, faster every day. Combine these two effects, and the satellite clocks drift by 38 microseconds every single day. It sounds like nothing, but light travels 300,000 kilometers in a second. If engineers did not correct for Einstein's predicted error, your GPS accuracy would drift by 10 kilometers every day. You would be lost within minutes. Every time your phone pinpoints your location, it is a silent tribute to that patent clerk in Bern. It is proof that we do not live in a common-sense world. We live in a relativistic one. We lost the comfort of absolute time. We lost the safety of the ether. But in exchange, we gained the keys to the cosmos. We realized that we are not merely observers on a fixed stage, but travelers on a rippling ocean of space-time. Guided by the constant, unwavering beacon of light.